since I already have it ready. Alright, so today is mostly going to be a crash course on trig. Because when it comes to teaching trig in college algebra, there's kind of this catch-22, where you want your trig to teach your algebra. You want to be able to use some trig as you're teaching algebra, but you also want to use some algebra when you're trying to teach trig. And so it's very common that when you're doing your algebra courses, they kind of throw in the basics of trig early on. And so that's kind of what we're doing today. Basics of trig is mostly what we're focused on here today. Make sense? Okay. So the first thing we're going to introduce is a coordinate plane, hopefully pretty familiar for you guys, often referred to as the xy plane. Now, how does the coordinate plane or xy plane work? We take a directed line segment this way, we call this a positive direction, this a negative direction. We take a positive segment this, or a directed line this way, we call this a positive direction, this a negative direction. We refer to this line as the x-axis, we refer to this line as the y-axis. We line them up so that they're perpendicular to each other, right? And now, the whole point of this is we want to assign numbers to points. And students kind of get this mixed up in their heads, the difference between numbers and points. Because you're used to thinking about 2, 3 as a number, or as a point. Now that's an ordered pair. That's not a point. What's a point? This is a point. But you're already real comfortable with the notion of we can somehow use numbers to represent points, or points to somehow represent numbers, this back and forth, and that's what we get from this coordinate plane. So this is what justifies our ability to do that, is what we're covering here today. And so when I talk about the point 2, 3, it's understood that that's not really a point, but these are the coordinates to some point in this plane. Because this right here is a plane, this is actually a geometric figure. 2, 3, in parentheses, those are just numbers. So those are just numbers. Over here we got a plane, which is an actual geometric figure. We're combining the two together with the xy plane or the Cartesian coordinate plane. So how does this work? We pick any point on the plane, like a point right there, and we're going to assign it coordinates x, y. Now what is x, what is y? X is the directed distance that our point is from the y-axis. So this directed distance from here to here is x. It's a directed distance. So it's positive this way. If we were talking about a point over here, then that would now be a negative distance. So x is the directed distance from your y-axis to your point. Y is the directed distance from your x-axis to your point. And so we signify a point with coordinates x, y. Make sense? So we'll plot some points really quick that the author gives us. So they say point P has coordinates 3, -1. Where's that? So it has to be a distance, a directed distance 3 from our y-axis and -1 from our x-axis. So here we are on our y-axis. We always start at the origin where these two intersect. We need to go 3 units away from our y-axis, directed distance. So positive distance means this way, 1, 2, 3. And then we need to go -1 distance away from our x-axis. -1 gives us a point right there. So the point right here is the point P. And P has these coordinates. Over-explaining it? One more? Alright, coordinates -2, 5. Where's that? -2, we need to go a directed distance of -2 from our y-axis, 1, 2. And then we need to go a directed distance of 5 from our x-axis. 1, 2, 3, 4, 5. And that's a point right there, our point Q. So that's the xy plane. That's how we associate to every point in the xy plane a pair of 2 real numbers. So if I give you a pair of 2 real numbers, you could find the corresponding point in the xy plane. Similarly, if I pick any random point in the xy plane, like that point, you can assign it a pair of real numbers. Namely, for this one, that's 2 over and 2 up, so 2, 2. So there's a one-to-one relationship between the points in the xy plane and the ordered pairs of real numbers. Sorry, I just threw ordered pair out of nowhere. We refer to these as an ordered pair. If I do parentheses, some number, comma, some number, and parentheses, that's what we mean by an ordered pair. Make sense? Okay, so that's the basics of the xy plane. Some verbiage that's often used. This number on the left-hand side we often refer to as the x-coordinate. We also refer to it as the abscissa. abscissa. The right-hand one we often refer to as the y-coordinate, and we also refer to it as the ordinate. So abscissa and ordinate, or x-coordinate, y-coordinate. This particular author likes saying abscissa and ordinate, as opposed to x-coordinate and y-coordinate, which is what more modern books do. Okay, so that's the basics of the xy plane. And now we're going to prove some trigonometry for the xy plane. So we're going to do a bunch of basic trig now, and for all basic trig, we need to start out with the Pythagorean theorem. So first thing we're going to prove really quick is the Pythagorean theorem. So how do we prove the Pythagorean theorem? Start by making two squares that are supposed to be the same. And see if I can make this picture decent. So I may call the distance from this point to this point B, and the distance from this point to this point A. And then I meant to draw this picture. Don't let my picture lie to you, but this is also supposed to be A, this is also supposed to be B, this is also supposed to be A, this is also supposed to be B, this is also supposed to be A, this is also supposed to be B. Make sense? Similarly over here, that was A, B, B, A, B. Good so far? Okay, now this is a square, since what is the side length of, what is this side length right here? A plus B, right? That's this distance. The length of this is A, the length of this is B, so the side length of the whole square is A plus B. Same with that side, same with that side, same with that side. And since it's a square, we know that all these are right angles. Right? And so the area of this whole square is A plus B squared. That's the area of the total square. Similarly, that's a right angle, that's a right angle, that's a right angle, that's a right angle. This is also a square with side lengths A plus B. So this is also A plus B squared is the area of this whole square and the area of this whole square. Good so far? Now on this left-hand square, we're going to create a bunch of right triangles. And I'm going to call the side length of this right triangle right here C. Good? C is the distance from here to here. Okay. Now, notice something. This is a right triangle. So this angle right here, well, what's the best way to say this? Going back to geometry, our theorem for congruence of triangle, one of our congruency theorems is side angle side, right? If two triangles have the same side length, the same middle angle, and the same side length again, the two triangles are congruent. Right? You remember that? Have you gone over that? Okay, so then this triangle, notice it has A, right angle, B, A, right angle, B. So this triangle is congruent to this triangle, which means that this is also side length C, and this is also side length C, and this is also side length C. So this internal shape right here is a... We don't know it's a square yet. We just know so far that it is equilateral. Equilateral? A rhombus. There we go. Yeah. It's a rhombus. All we know is the side lengths are equal. We don't know that this right here is a right angle yet. We need to discover that that's a right angle. We need to prove that's a right angle, right? Well, I know that this triangle is congruent to this triangle, which means this angle right here is the same big as this angle right here. And this angle right here is the same big as this angle right here. Right? So what does this middle angle have to be? The difference between them. Right, maybe let's name these really quick. We'll call this angle right here capital A, and we'll call this angle right here capital B. You with me? And this is also capital B, this is also capital A. Now I know that A plus B is equal to what? Look at this triangle. What's the sum of all the angles in a triangle? 180. 180. So then angle A plus angle B has to be? No.
Plus 90 is 180.
Yeah, angle A plus angle B plus 90 is 180. Okay. So what's angle A plus angle B have to equal? 90. Perfect. Now a straight angle, which is this whole side, is what in terms of degrees? 180. So A plus B is 90. This plus this plus this all has to be 180. So how big does this internal angle have to be? 90. And so that's a right angle. And similarly, that's a right angle. And similarly, and similarly. And so this inside is actually a square. And so we proved so far that inside here we have a square. Good? Okay, so that's the hard part of the proof. So now let's add up the areas, all the areas of the figures inside of here. So notice that we have 4 identical triangles, and then we have this square with its area. What's the area of this square? We do know. If I say here's a square, and I say it has side length 2, what's the area of the square? If I say it has side length A, what's the area of the square? And if I say it has side length C, what's the area of the square?
C squared.
Perfect. So the area of this internal square is C squared.
Yeah.
Wonderful. What's the area of this triangle?
1/2 A times B.
We have 1/2 A times B is the area of this triangle, but we have 4 of those, right? So I have 4 of those plus C squared is my total area. Okay, good. Now over here, let's draw some pictures. I'm going to connect these lines like that and those lines like that. What's the area of this?
B squared.
B squared. What's the area of this?
B squared.
A squared. What's the area of this?
AB.
And what's the area of this?
AB.
Perfect. So the total area of this is A squared plus 2AB plus B squared. Now I know that the area of this whole square is also A plus B squared, and I know the area of this whole square is also A plus B squared. So I know that these two have to have the same areas. In other words, I know this is equal to this. And so simplify over here really quick. 4 times 1/2 is 2, so we have 2AB plus C squared is equal to A squared plus B squared plus 2AB. I just moved the 2AB to the end, right? And then subtract 2AB from both sides, and I get A squared plus B squared is equal to C squared. Pythagorean theorem. If you have a right triangle whose legs have side length A and side length B, and whose hypotenuse is side length C, then you have this equation. Make sense? Wonderful. So that's Pythagorean theorem, and that's one of the most basic theorems we need to start trigonometry, is the Pythagorean theorem. So there we go, prove the Pythagorean theorem. So now let's move on to talking about radians. Have you ever talked about radians before? You know degrees but not radians? Okay, so let's talk about radians. So we're going to start out with some circle. Here's some circle, and it has a radius just little r. If we talk about its distance from here to here, then we call that d, right? And so d is equal to 2r. And then we typically use c to talk about its circumference. C is the distance all the way around the circle. So d is the distance to go from here to here. C is the distance to go from here back to where you start. That's the difference, right? Okay, have you ever learned what pi is? What's pi?
Well, it's a number.
What number?
Like 3.14 or something.
How did you come up with that number? What's that number approximating?
The circle number.
You don't know? So pi, by definition, is equal to circumference divided by diameter. So it's the ratio of this distance to this distance. And for any circle you draw, its circumference is roughly 3.14 times as long as its diameter. So if I were to draw a circle here with a diameter, we'll pretend that that's 10 inches, then the circumference is roughly 31.4 inches. Make sense? Okay, and we can also say that as c over 2r if we write it in terms of r. Or in other words, circumference is equal to pi r. And that's probably a formula you've seen a lot for calculating the circumference of a circle. 2 pi times the radius. Good so far? Okay, now we're going to go from talking about radiuses to talking about radians. Radians is another way of measuring angles. The same way I can measure distance with feet, or I can measure distances with meters. What's better, feet or meters?
Meters.
Meters are better. What's better, inches or centimeters?
Inches.
Centimeters. Think about converting miles to inches. How do you convert miles to inches? You start with a mile, you say there's 5,284 feet in a mile, and then there's 12 inches in a foot. Now think about converting kilometers to centimeters. How many meters are in a kilometer? 1,000. How many centimeters are in a meter? 100. Which of those are nicer to work with? Meters, centimeters, kilometers, the metric system. Feet and inches, that's ugly. Now I guess you haven't had to do a lot of problems yet where you've had to work with the various ones, but once you do, you'll fall in love with the metric system. So similarly, you've been taught to measure angles in terms of degrees. And it turns out that's a terrible way to do it. And it makes life hard. And there's a much better way to talk about angles, which seems a lot harder when you first come across it, but it's actually way better in the long run. And that's called radians. So let's get a sense for the difference between radians and degrees. And we're going to just start talking about it. We'll just make a table comparing the two. So 360 degrees gets me all the way around the circle, right? How many radiuses would I have to use to get all the way around the circle? So if I took one radius and I laid it out, that would get me this far, right? And another radius would get me like that far. So this is 2 radiuses. Here's 3 radiuses. How many radiuses do I have to use to get all the way around this circle? Probably like 6. But if I want to get the whole circumference, how many radiuses do I need? 2 pi. If I have 2 pi radiuses, I have the circumference. So 1 radius gets me this far, 2 gets me this far, 3 gets me this far, 3.14159 gets me this far. 4 gets me this far, 5 gets me this far, 6 gets me this far, and 3.28 blah 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 gets me this far. You with me? So it's 2 pi radiuses. Or if we talk about it in terms of angle, so radiuses is measuring out this distance. If we're talking about the angle, we call it 2 pi radians. And I'll put RAD here for radians, so it's an angle measure. So rather than calling going all the way around the circle 360, we're going to call going all the way around the circle 2 pi. You with me so far? Okay, so let's play around with this for a second. How many radiuses do I need to get halfway around the circle? Which is the same as 180 degrees. 1 pi. So it's pi radians. This angle from here to here is pi radians. What if I just wanted to go 1/4 the way? Pi halves. Perfect. And so we're actually going to jump over here and start populating our unit circle. I'm going to write the degrees, and then you're going to give me the radians. Have you ever seen the unit circle before? Is that something you've ever heard? You'd remember if you had, probably. So probably haven't. All right, so this angle right here is 30 degrees. I want you to tell me what it is in radians now. Almost. Pi over 3 is right here. That's 60 degrees. Degrees is how much of 180?
1/6.
So, in radians, it's going to be
Pi over 6.
pi 6. Now, I'll give you my own trick for how I personally think about it. degrees is what portion of the whole circle? 1/12. And pi is half a circle. So 1/12 of the circle is, if you take 1/12 and you multiply it by 2, is that how I think about it? Kind of. 1/6 of a half is the way that I think about that. Pi is a half, we take 1/6 of a half, which is 1/12. That's the way I think about it. But whatever helps you think is whatever helps you think. So now let's jump over here and do this one. This one's 45 degrees. Or in terms of radians is okay, let's jump and do some easy ones first. Probably should start with the easy ones. This right here, I'm going to call 360 degrees rather than 0 degrees, just because. So 360 degrees in terms of radians is what? How many radiuses does it take to get to there? 2 pi. Perfect. And over here, where we have 180 degrees, this is pi, which is 180 degrees. Okay, straight up and down, which is 90 degrees. Pi halves. And then over here now is pi fourths. Perfect. Pi fourths. This one right here is pi thirds, which is 60 degrees. Pi thirds. Over here. Not pi thirds. This isn't 60 degrees again. If pi thirds gets me this far, what gets me this far? How much bigger is this angle than this angle? Double. So what's the answer? 2 pi thirds, that's it. I think you were overthinking that somehow. Okay, this one right here, this is 135 degrees. Or,
2 pi fourths.
not 2 pi fourths. If you double pi fourths, that gets you right here. 3 pi fourths. All right. Here was pi fourths, 2 pi fourths, 3 pi fourths, 4 pi fourths, which is the same as pi. And then all the way to 8 pi fourths, which is the same as 2 pi. Perfect. This one, which is 150 degrees. Four pi 6 is the same as 2 pi thirds. 5 pi 6. If this over here is pi 6, then this is pi 6 less than pi. So you subtract pi 6 from pi. Or however you think about it. Okay? And then filling in the bottom, we won't worry about that. I think you're starting to get a feel for this. Now you might be thinking, why on earth would we ever use these ugly way of talking about angles when we already have degrees, which is way better, right? Maybe. So let me ask you a question now to help motivate this. Let's say that we have a circle track here, so people are running around this track, okay? And we'll say that the circumference of the track, or the radius of the track is 10 meters. And we'll say that a person runs 135 degrees around the track. So they started here and they ran 135 degrees around the track. How far did they run?
3 pi 4 times 10.
You see what you did? Clever. You went straight to this. And that's the beauty of radians. If I want to go from my angle to my distance, I just multiply the angle by the radius. And so this arc length, we typically use S for arc length, the distance from here to here, S, is always equal to R times theta, as long as theta is in radians. This is only true in radians. If you plug that in with degrees, this is no longer the case. You see that? And it turns out calculating distances along circles is something we do all the time the further you go in maths. It's absurd how common we do that. And that's why radians are so great. Because even when you're not talking about circles, you're talking about things like waves, you're still kind of talking about circles. So circles shows up a lot the further you go in maths, even sometimes behind the scenes. So that's why radians, and that's what radian is. Okay, so now let's get down to our definition of sine and cosine. Sine and cosine. So draw some circle, and we draw what we call the unit circle. Unit circle means our radius is 1. You with me? That's why unit, a single unit circle, a 1 radius circle, the unit circle. Pick any point on the circle, and it's going to be at some angle theta, right?
What is that?
What is theta? Some angle, might be like 60 degrees, doesn't matter. Some angle, and this has coordinates x comma y. Good so far? All right, by definition, we call cosine of theta is the x coordinate of that point. And sine of theta is the y coordinate of that point. You with me so far? So let's try one. Let's say that I tell you theta is 90 degrees. So I want you to find me cosine of 90 degrees. Sorry, I'm being super lazy here, and I shouldn't be. Let me be more clear. Cosine is a function, and its input is an angle. So we should really have parentheses like that. The same way that you've seen something like f of x is equal to 2x squared plus 4, whatever, some function. Cosine here is some function. What does it look like? Not particularly important. Let's see if I can remember it for cosine. Maybe Emma can help me remember.
Starts at the origin.
Yeah, it starts at 1, right?
I think that's sine.
No, cosine starts at 1.
Sorry, yeah, you're
So
right.
it's going to be something like 1 plus, or 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial, going on forever.
Oh.
Something like that. I'm not sure that's exactly it. What exactly that function is, we don't really care about. But the point is, it is some function. Just like this is some function. You with me? So you're never going to use this to actually calculate its values. You're going to use the definition that I gave you to calculate its values, which is just find, for cosine, just find the x coordinate at that angle on the unit circle. You with me? So let's try this really quick. So I said, for example, let's find cosine of, well, we'll start with 0 degrees. Cosine of 0 degrees. So let's make an angle of 0 degrees. That's this angle right here, right? What are the coordinates of this point if this has radius 1 and we draw our xy system through the origin like that? 1 comma 0. So what's the x coordinate? 1. So cosine of 0 degrees is 1. What's sine of 0 degrees? 0. So let's actually start populating what we call our unit circle over here. So this right here is a unit circle. It has radius 1. So the coordinates of this point are 1 comma 0, right? What's the coordinates of this point? Perfect. Negative 1, 0. What's the coordinates of this point?
0, 1.
0, comma 1. And what's the coordinates of this point?
0, -1.
Perfect. All right. So now with those 4 points, notice that I can start asking you some questions. I could ask you something like, what is the cosine of pi? -1. It's the x coordinate. Or I could ask you something like, what is the sine of 3 pi halves? Oh, we didn't mark that one. Sorry. We'll just say pi halves. 1. Or I could ask you something like, what's the sine of 90 degrees? One. What if I ask you something like, what's the sine of 87 degrees? Now, 87 degrees is going to be like right here, right? And so it's going to be slightly less than 1. What's it going to be? You don't know. Emma doesn't know. I don't know. Anyone watching this doesn't know, unless they're really weird. So for the majority of the times that you see sine and cosine functions, we don't know the answer. And so we only give you very special angles that we know the answers to. Like 0 degrees, or 90 degrees, or 180 degrees, or 270 degrees, or 360 degrees, or 540 degrees, etc. So you should only know how to calculate these values for very special angles. And in general, you should not know how to give me the answer, but your calculator does. So even students who have taken trig, if you go ask them what's the sine of 87 degrees, they're not going to know. And that's normal. So you only know what these functions give you in very special cases, and even the few very special cases that we're going to talk about turns out to be really, really, really useful. So the only angles that we're going to talk about are the ones I have marked here on my unit circle. 30 degrees, 45 degrees, and 60 degrees. And then it's basically a repeat over and over again after that. You with me? So that's going to be our job for the remainder of this, is to try and come up with the coordinates of each of these points. Good? Okay, so we're going to start by trying to find the coordinates to this point right here, the 45. That one's the easiest. Now here's what I'm going to do. I'm going to draw a triangle that starts here, goes up to that point, and then drops perpendicularly down to here. So that creates a right triangle. I'm going to draw that triangle to the side over here. So here's that same triangle to the side. My picture is going to lie. Trying to make it lie a little bit less. So 45 degrees, or pi fourths, here. This is the coordinates that we're talking about. So this is this triangle moved right here. This is a right angle. Maybe do 45 degrees. You're going to be more comfortable with that. So let's stick with that for a second. Right? You understand the triangle I'm talking about? So we're looking for the coordinates of this point. We're looking for the coordinates of this point, right? Which, if we were to draw this triangle, it would be this distance and this distance. Your x-coordinate is this distance, your y-coordinate is this distance. So drawing this triangle over here, the length here is your x, and the height here is your y that we're looking for this point, x comma y. So if this point has coordinates x comma y, then for this triangle, this distance here is x, this distance here is y. You with me? Okay, I know that this is 45 degrees, I know that this is 90 degrees. What else do I know?
The whole triangle is 180 degrees.
Okay, so what's this angle? 45. Or in other words, this angle and this angle are the same size. So I'm going to erase 45, we don't really care about that anymore. The point is this angle and this angle are the same size. So what kind of triangle is this? Isosceles. It's an isosceles triangle. What do you know about an isosceles triangle? You know that the bottom angles are equal, but what else do you know?
The y and x are equal.
Y and x are equal. So I can replace y here with just an x and we're still fine. You with me? What else do I know about this triangle? The last thing I need to remember about this triangle is it came from this circle, the unit circle. So what is this distance from here to here?
A squared plus the sine.
It came from this triangle, or from this circle. What's the radius of this circle? 1. It's a unit circle. What's the distance from here to here? 1. This is the radius. This is this. You with me? So this has distance 1. This is a right triangle, so I know I can use the Pythagorean theorem. So I know that this side squared plus this side squared equals this side squared. So I know x squared plus x squared is equal to 1 squared. You follow that? Or in other words, 2x squared is equal to 1. Or in other words, x squared is equal to 1/2. Or in other words, x is equal to the square root of 1/2. Or in other words, x is equal to the square root of 1 over the square root of 2. And I'm going to multiply this side by 1 now. I'm going to multiply it by the square root of 2 over the square root of 2. You with me so far? So x is equal to, what's the square root of 1? Times the square root of 2. It's just the square root of 2. Anything times 1 is just that thing. SpongeBob times 1 is, there you go. So square root of 2 times 1 is square root of 2. What's square root of 2 times square root of 2? What is the square root of 9?
3.
How did you get that?
Because 3 times 3 is 9.
What is the square root of 2 times the square root of 2? This number, square root of 2, is a number such that when you multiply it by itself, you get 2. So the square root of 2 times the square root of 2 is
2.
just 2. And we call that rationalizing your denominator. Okay, so we figured out what x is, but now what's y equal to? Square root of 2 over 2. Perfect. So this was also y. So we found our xy coordinate. It's square root of 2 over 2, square root of 2 over 2. So square root of 2 over 2. Square root of 2 over 2. So if you were to take your calculator and you were to plug in cosine of 45 degrees, it would spit out square root of 2 over 2. Similarly, if you were to take sine of pi fourths, what would you get? Square root of 2 over 2. Root 2 over 2. Now notice that the square root of 2 is less than 2. Because what's the square root of 4?
2.
Huh?
2 times 2.
What's the square root of 4?
2.
2. So the square root of 2 has to be less than 2. And what's the square root of 1?
1.
So the square root of 2 has to be more than 1. So root 2 is somewhere between 1 and 2. It's somewhere in between. So when I take a number between 1 and 2 and I divide it by 2, then it's going to be some number. It's not going to be, it's going to be between 1/2 and 1. Since the square root of 2 is between 1 and 2, then the square root of 2 over 2 is between 1/2 and 1. Which kind of makes sense. Look at this. What is this distance?
1.
This is 1, half that, here's 1/2, here's 1, and so it's somewhere in between. Root 2 over 2. So, kind of makes sense. No obvious problems with it, right? Okay, so now let's jump ahead and look at this point right here. What are the coordinates of this point right here?
Square root of 2 comes square root of 2.
Almost. First off, you meant square root of 2 over 2, right? No? Notice that this point is going to be the same height as this point.
Yeah.
So they have to have the same height. So their y-coordinate has to be the same.
Oh, I know what the answer is.
So that's root 2 over 2, right? Now, if I were to make this triangle, how does this distance compare with this distance?
It's negative.
It's negative. So negative root 2 over 2. Perfect. And we could have now, what about for this point right here? So this point right here, should we really quick plug in the rest of these degrees?
Sure.
So this one right here is 210 degrees. This one right here is 225 degrees. This one right here is 240 degrees. This one right here is 270 degrees. This one right here is 300 degrees. This one is 315 degrees. This one's 330 degrees. Oops, degrees. Right? And then let's plug in their pi components really quick. This is 7 pi 6. Just counting by 6. Here's 5 pi 6. Here's 6 pi 6. Here's 7 pi 6. Here's 8 pi 6. 8 pi 6. Here's 9 pi 6. 9 pi 6. Here's 10 pi 6. And here's 11 pi 6. And then finally, counting by fours, we have 3 pi fours, 4 pi fours, 5 pi fours, 6 pi fours, 7 pi fours. Right? And then 8 pi fours. Okay, so we got all those plugged in. So now I could ask you for something like, what is the cosine now of 3 pi fours? Negative root 2 over 2. Right? Perfect. So I think you're getting the hang of this. And so trig students, when they go take trig, they're told that they need to memorize this table. And they need to memorize the table because they have to compute cosine and sines of a lot of these angles over and over again throughout the class. Okay, let's finish putting in coordinates now. So what are the coordinates now at this point right here?
Negative root 2 over 2.
Perfect, it has the same x coordinate as that point. What's its y coordinate?
Negative root 2.
Perfect. Now let's jump over to this point.
Root 2 over 2. Negative root 2 over 2.
Wonderful. Okay, so now the only points we're missing are these points, right?
Yeah.
So we just need one more triangle to get those points and we'll be done. Now the triangle I'm going to use is for this point right here. So I'm going to be talking about the triangle when you drop down that perpendicular to there. With me? Okay, so trying to approximate that triangle over here. That's a right angle. What's this angle?
6, 30.
So what's this angle?
30.
30. And what's this length? 1. Perfect. And then this is x, this is y. That's what we're looking for. We're looking for the coordinate x comma y for this point, right? Okay, so for this one, what I'm going to do is I'm going to reflect this triangle over this way. So reflecting it over that way, we get this. And since it's a reflection of this triangle, this angle right here should also be 60 degrees. My picture is lying to you. And then this angle right here should also be 30 degrees. You understand what I did?
Yeah.
And this side length right here is
1.
1. Okay, perfect. So what's this angle?
60.
What's this angle?
60.
What's this angle?
60.
So what kind of triangle is this?
I don't know the name of it.
An equilateral triangle? Okay. So what is x?
1.
X is the distance from here to here.
2.
1 half, right? This distance is 1. X is half that. So x is equal to 1 half. And now we just need to figure out y. So x we know is 1 half. Now we need to figure out our y. With me? Okay. So now, replace x here with 1 half. How can I figure out what y is if I know that this is 1 half and this is 1?
Fine. Wait. Just use the Pythagorean theorem.
The Pythagorean theorem. So tell me what to write.
1 half squared times y squared equals y squared.
And that is very off.
And 1/2 squared times y squared equals.
Why are you saying times?
Plus.
Plus, okay. Now, if I gave you a triangle like this, here's our right angle, and I call this A, and I call this B, and I call this C, what does the Pythagorean theorem tell me? That A squared plus B squared equals C squared, right? Let's see if that makes any sense. Which of these numbers are the biggest? A. So you're telling me A squared plus something is equal to C squared? No, that makes 0 sense. And that's why you don't memorize the Pythagorean theorem as A squared plus B squared equals C squared. It's the square of the length of the legs are equal to the square of the hypotenuse. And you, like every single high school student now, gets completely confused if I just refuse to call that side C. Since I called it A, you still tried to use this formula, which is not right. So what is the correct formula? It's B squared plus C squared equals A squared in this example. The shorter side squared is equal, when you sum up the shorter side and square it, you get the same thing as the longer side squared. Right? This one makes 0 sense. A is bigger than C. So think about it, don't just recite a formula, or you're always going to be wrong in my class. Because I intentionally do stuff like this. So you'll stop and actually think about it. Okay, so now look at our triangle. And tell me exactly what to write.
1 squared plus y squared equals 1 squared.
Much better. Because that's correct. Okay, so now let's just simplify this. So what is 1/2 squared?
1/4.
1/4. So we have 1/4 plus y squared is equal to 1, right? Subtract 1/4 from both sides, and I get y squared is equal to 3/4. So y is equal to the square root of 3 over 4, which is equal to
Square root of 3 over square root of 4.
okay, which is equal to
Just multiplying by square root of 4.
what is this?
Oh, 2.
There you go. Root 3 over 2.
Yeah.
Perfect. So this is root 3 over 2. You with me? Now remember our initial triangle, so let's go back to our initial triangle. And what did we just barely find? We found out that that was 1/2 if this is 1, and this is root 3 over 2. Right?
Yeah.
Now notice what happens if I take that triangle. I'm going to do some flipping of it, see if you can understand what I'm going to do. I'm going to take this angle and flip it like that. So I'm going to draw it so that my 60 degrees is up here and my 30 degrees is down here. So now it looks like this. My picture lies a lot, but now this is our 30, this is our 60, this is still our 90. What's this length over here?
1/2.
1/2. And what's this length?
Square root 3 over 2.
Perfect. So notice now this triangle is exactly what we get if I drop my perpendicular down from here. So now what's the coordinates of this point?
And then 3 square root of 3 over 2 comma 1.
Perfect. And notice, it kind of makes sense. I mean, you can't trust my picture too much, so actually it doesn't really make sense. Sorry. This seems like it makes closer sense with this one. That when you drop that down, that gets you about halfway between them, right? Now my picture doesn't do as good of a job as showing that this is halfway up. but it gets pretty close. So if I drew a better picture, things would line up better. Anyways, so now what's the coordinates of this point?
-1/2. Root is 3 over 2. Negative root is 3 over 2 1/2.
Perfect. And then you know how to fill in the bottom. Alright, so now we'll test you. Ask you for something like the cosine of Pythagorean. One half. And now you see why trig students memorize this unit circle. Because they get stuff like this all the time. Or you need to calculate the sine of 3 pi fourths. Root 2 over 2. Wonderful. So, I think you got that down. You now understand what the unit circle is. Now, we need to introduce you to the rest of the trig functions. Okay, so if we were on a unit circle, so this has side length 1, and this is angle theta, then the x-coordinate here is the x-coordinate of this point, or this distance if you prefer. What's this distance? But how would you calculate it? If I gave you theta, how would you figure it out? You'd plug it into which function? What I'm getting at is this is just cosine of theta. Look, if I ignore that for a second, let's go back. I say find me the cosine at pi fourths. What is it? Root 2 over 2. What did you do? You said, what is the x-coordinate at the angle pi fourths? Root 2 over 2. Or what is this distance when our angle is pi fourths? So when your angle was pi fourths, you calculated this distance by finding its cosine. Similarly, how would you calculate the height? Sine. Yeah, you probably don't remember the names.
Yeah.
Sine of theta. And this is for coordinates x comma y, right? And so on the unit circle, then x is equal to cosine of theta, and y is equal to sine of theta. If you pick any point x comma y on the unit circle, whether it's here, 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 it doesn't matter. If I give you the angle to that point, you can give me the x and y coordinates. Right? So this distance, if my unit circle is 1, then this distance is cosine, right? What if I stretch out my circle so it has a radius of 2? Then what's this distance going to be?
Is it going to be 2 cosine?
2 cosine theta. And this distance is going to be 2 sine theta, right? And what if I were to stretch it out so it had a radius of 3? Then how big would this distance be?
3 cosine theta.
And if I stretch this out so it has a radius of little r, then what's this distance going to be? R cosine theta. Wonderful. And this is over here is going to be r sine theta. Good? Now, the final thing to see is erase the circle. So you only have the triangle. And erase that point. So if you have some triangle, that's a right triangle, has to be a right triangle, and you know this angle, and you know the hypotenuse of the triangle, you instantly know the length of this side, and you know the length of this side. The length of this side is r cosine theta. The length of this side is r sine theta. Let's try an example really quick. I'm going to give you a triangle. This right here is 3, and I tell you that this angle right here is 45 degrees, and that's a right angle. How big is this side? 3 cosine of 45 degrees, but you know the cosine of 45 degrees. So how big is this side? 3 squared to 2 over 2. So if this is 3 meters, then this is 3 squared to 2 over 2 meters. And so if you were actually out and you need to measure out, and I triangle like this for some reason, here's how you can do your measurements. Figure out what that length's going to be. You with me? Okay. So I'm going to draw a triangle now. It's a right triangle, always and forever. This is going to be some angle theta we don't know, some radius r, x, y. Usually they said x is equal to r cosine of theta, right?
Yeah.
And y is equal to r times sine of theta. So if I take this equation and I solve for cosine of theta, I get cosine of theta is equal to x over r. And I get sine of theta is equal to, sorry, I'm going to stop writing parentheses. You're going to have to get used to that. Can't help it. No one ever writes parentheses. But it is a function, so that's why I try to remember. But sine of theta is equal to y over r, right?
Yeah.
And this is probably how they were first introduced to you. Cosine of an angle gives you the adjacent over hypotenuse. Sine of the angle gives you the opposite over the hypotenuse. Were you taught SOHCAHTOA? Oh, you weren't? Okay, now I don't even need to make that connection. Okay. So we've got this triangle, and these are the 3 lengths. You know that if I give you x over r, that is now cosine of theta. And y over r is equal to sine of theta. Now, that is 2 of the possible ratios I can construct with these 3 numbers. What are all the possible ratios I can construct with these 3 numbers? I can do x over r, that's one ratio. I can do y over r, that's another ratio. I can do y over x, that's another ratio, right? And so we have a name for that ratio, y over x. We call that tangent of theta. I could also do, instead of x over r, I could have done r over x, right? And we call that one secant of theta. I could have also done r over y, and we call that, oh, sorry, that's cosecant. No, that is secant, sorry. This is cosecant of theta. That's CSC of theta. And then finally, we could have also done x over y. And we call that cotangent of theta. So these are your 6 trigonometric functions. And they all encode a different ratio. Typically, mostly we work with these 2. This one shows up quite a bit. These 3 we hardly work with. But these are our 6 trigonometric functions. Why are they called trigonometric functions? They're the 6 functions about triangles. Trigonometry is the study of triangles. That's what it means. And so ultimately, these are what we're interested in. Now, we can also express these functions instead of in terms of these ratios. We can also express them in terms of these functions. Notice that secant is just a reciprocal of cosine. Cosine's x over r, secant's r over x. So it's the same thing as 1 over cosine of theta. Sine of theta is y over r. Secant of theta is r over y, or in other words, it's 1 over sine of theta. Now tangent, a little bit different. Notice tangent is y over x. But let's look at sine of theta over cosine of theta really quick. What's sine of theta equal to?
Wow.
Huh?
Y over.
Y over r. What's cosine of theta equal to?
X over.
What does it simplify to?
X over Y.
If I take a fraction and divide by another fraction, that's the same as multiplying by the reciprocal. Right? So it's the same thing as y over r times r over x, which is equal to,
Y over X.
the r's cancel out.
Oh, Y over X.
So just y over x, which is the same thing as tangent. See that? So sometimes tangent of theta is defined as sine over cosine. Sometimes it's defined like this, as y over x. Doesn't matter which way you define it, they're equivalent. But we like to describe mostly we use cosine and sine, and then we describe these other functions in terms of cosine and sine. So I could define it as this ratio, but I could have also defined this as 1 over cosine. I could define this as this ratio, but I could also define it as 1 over sine. I could define tangent as this ratio, but I can also define it as sine over cosine. Similarly, cotangent is just a reciprocal of tangent, so I could also define cosine of theta over sine of theta as cotangent of theta. Make sense? Now I know that's a ton to take in, and there's a lot going on there. There's 3 important points to take away. Cosine gets you your x coordinate, sine gets you your y coordinate, and then what does tangent get you? This is the last interesting one. It gives you y over x. And you have a name for that from your early algebra courses. What do we call this distance over this distance? Sometimes you call this the rise, sometimes you call this the run. What's rise over run? Slope. So tangent of theta also gives us our slope. So cosine is how we get our x coordinate, sine is how we get our y coordinate, tangent is how we get our slope. And then the rest of these 3 we hardly ever use. They rarely show up. That all make sense? Okay. That was a big trig review, but that's it for our trig review. And that gives you all the trig that we're going to need in this class. Hopefully. That's more than the author covered in his appendix, so.
Did you need to go over the distance formula?
Oh, thank you. Yes, I was going to do that after Pythagorean theorem before I dived into all the trig. But we're fine doing it now because now we're jumping back into the book. So we covered all the trig. Now, going back to algebra, we're going to cover the distance formula, which is how we get the distance between 2 points. So going back into our coordinate system, if we have some point and we know its coordinates, so I've got some point here, P1, and I've got some other point here, P2, and I know that P1's coordinates are, P1's coordinates we'll call x1 comma y1, and P2's coordinates we'll call x2 comma y2. You with me so far? What is the distance then between these 2 points? So I know the height of this is y1, and I know the run of this is x1, right? And I know the height of this is y2, and I know the run of this is x2. Now notice that I can construct a mini right triangle right here. Right? So here's my little right triangle. That's a right angle. What is this side length? How long is this side?
X2 minus X1.
X2 minus x1, perfect. How long is this side?
Y2 minus Y1.
Y2 minus y1. And now we're looking for this distance, which we'll call little d. And how can we calculate little d? Pythagorean theorem. Tell me what to write.
X squared minus x.
I'm with you.
Minus x1 to the power of 2 plus y2 minus y1 to the power of 2 equals d to the power of 2.
Perfect. Now take the square root of both sides, and we get d is equal to plus or minus the square root of x2 minus x1 squared plus y2 minus y1 squared. Right?
Yeah.
Now we have no notion of a negative distance. We have directed distance, but we don't have negative distances. So when I talk about the distance from here to here, I'm always talking about the positive value, never the negative value. And so this is your distance formula. This gives you the distance between any 2 points. Have you come across that before? Not that you're sure of? You just got it really quick, so I wondered if you already knew it.
Well, I think I have, yeah.
Okay, so that's our distance formula. So now we can calculate the distance between 2 points. If I told you that this over here has, oh, I won't pick numbers that come out nice. I'll make up numbers that come out nice. So we'll say that this right here is 2. This right here is 5. We'll call this one right here 3. And we'll call this one right here 7. So this is point 2 comma 3. This is point 5 comma 7. You with me? So now we need to find the distance between those 2 points. We can just use this formula. So in that case, d is equal to the square root of the x-coordinate of this point. It doesn't really matter which point I call x1, x2. I could have swapped the order and it doesn't change anything. So just pick one point to call x1, y1. And to show you it doesn't change anything, I'm going to make this one x1, y1 and this x2, y2. Okay. All right, so we have x1 minus x2 squared plus y1 minus y2 squared. You with me?
Yeah.
Okay, so d then is equal to, what's 5 minus 2?
3.
Squared. Oh, I didn't do it.
You made it easy.
I couldn't even think about it right. I did something different than what I said I was going to do.
Yeah.
I said I was going to make that x1, x2. Oh well. Can't help but make them positive. But if we swap the order, then it's just negative 3, and then you square it and you still get 9. That's all that changes. So since you're squaring it, it doesn't matter which way we do it. But 5 minus 2 is 3, squared is 9, plus
4 squared is 16.
16. 9 plus 16 is?
5.
Square root of 25 is? 5. So the distance there is 5. So this has length 5. Make sense?
Mm-hmm.
Now normally the distances will be some ugly number. I pick numbers to make it come out nicely. Okay. Did I cover all the things I said I cover there? Cool. All right. So now we'll move over to talking about our examples. Let me come that way some in case I need to reference a bit of the unit circle. Oh. Okay. So let's do an example. Let's do this example first. Find the distance between the 2 points A and B, where A has these coordinates and B has these coordinates. You with me? So let's get a rough picture of what this looks like. Really rough picture. A is 2, negative 8. So 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. So here's our point A. B is negative 3, 4. So 1, 2, 3, 1, 2, 3, 4. Here's B, very roughly speaking. We're looking for the length of this line segment, right? Okay, how do we calculate that? Our distance is equal to the square root of, pick whichever point we're going to call our x2 and then whichever one we're going to call our x1. So I'll use this x2. So x2 minus x1 squared plus y2 minus y1 squared. Notice minus negative 8 makes it plus 8. Good? So that's equal to square root of 3 minus 2 is, or negative 3 minus 2 is negative 5 squared is 25. Plus 4 plus 8 is, squared is 144. 144 plus 25 is,
169.
and the square root of 169 is 13. So our distance is 13. Alright. Next one. Find P on the x-axis such that P is equidistant from A and B. Alright. So, draw our picture here. Try and be a little bit more careful about this one because it might matter a little bit more. How far over am I going to have to go? Alright. So A was at 5, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4. Here's A. B's at negative 2, 3. 1, 2, 1, 2, 3. Our job is to find a point P. P is going to be somewhere on here. P somewhere on the x-axis so that it's equidistant from both of these. You understand the problem?
Yes.
So this one, rather than calling it B, I'm going to just put its coordinates there. This is minus 3, 4. This one was 2, oops, no. It was these ones. Minus 2, 3. This one was 5, 4. And I need to find my point. If my point is on the x-axis, what's its y-coordinate? 0. So whatever this point looks like, it's going to be something like 0, comma, x, and I need to figure out what that x is. You with me? Now the distance from this point to here is equal to, so we'll call that d1. d1, the distance from this point to here, is equal to the square root of its x minus this one's x squared. So 0 plus 2 squared, if we write it out, plus, oh, sorry, that's where we have our x. Sorry. No wonder, I wrote this backwards. X comma 0. Okay, now our brains are straight. Alright, so this one's x-coordinate minus this one's x-coordinate squared, plus this one's y-coordinate minus this one's y-coordinate squared. Right? So that's d1, the distance from here to here. d2, the distance from here to here, is equal to the square root of, and we're going to have x minus 5 squared plus 0 minus 4 squared, right? Okay. Now we are trying to find the x that makes these two distances equal. In other words, that makes this equal to this. So I know that d1 has to equal d2. I'm looking for the x that makes that true, right? Which is also going to happen where d1 squared is equal to d2 squared. So let's write out d1 squared. d1 squared, that's x plus 2 squared plus 9, there's d1 squared, is equal to d2 squared, which is x minus 5 squared plus 16. And now we just solve this the same way we solve regular equations. So we're going to have to multiply this out and then move all our x's, or move everything to one side to 0, and then factor it, and we'll get our solutions. Okay. So multiplying this out, we're going to get x squared plus 4x plus 4, and then we have plus 9, maybe I'll subtract 9 from both sides as we go, is equal to, when we square this thing out, we're going to get x squared minus 10x plus 25. And then when we took away 9 from 16, we were still left with 7. Follow everything I did there? Okay. Now notice, x squared, subtract x squared from both sides. That's gone. And now I'm going to move all my x's over here and all my constants over there. So I'm going to plus 10x to both sides. So over here we now have 14x is equal to, and I'm going to move this 4 over here, which is going to make it negative 4. So 25 plus 7 is?
32.
And then minus 4 is? 28. Or in other words, x is equal to? 2. So it's going to be this point is a point equidistant from those 2 points. Pretty cool that we can figure that out, right?
That's the 3.
Oh, yeah.
Okay.
Pictures lie. Yep. This would have been the one equidistance between both of them. Good. Yeah, don't trust my words, trust the math. Okay, so did those examples. Find the locus of points with an abscissa of 5. What on earth does that mean? Find the locus of points with an abscissa of 5. What does abscissa mean? The x-coordinate.
Oh.
So if we're saying find the locus of points with an abscissa of 5, we're saying find the locus of points whose x-coordinate is 5. And so what does that look like?
5 y.
Yeah, 5 comma y, so all the points 5 comma y, right? What are all the points that satisfy that? Let's come at it a different way. So let's draw our picture here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we go over 1, 2, 3, 4. So I pick this point right here. And this point has 4 comma negative 1. Does that have an abscissa of 5?
No.
Okay, so that point's not in our locus. Okay. What about this point? 5 comma 0. Does that have an abscissa of 5?
Yes.
Okay, so that point is. What about this point?
No. It's just going to be a vertical line.
It's just going to be a vertical line. And that's it. You understand what we mean by locus? A set satisfying some condition. So, find the set of points satisfying the condition x equal to 5. Okay? Let P1, P2 with coordinates x1, y1, x2, y2 be points on a non-vertical line with an inclination of theta. Then the tangent is going to be y2 minus y1 over x2 minus x1. So let's draw this out and make sense of it. So we've got some line, somehow, non-vertical line. So draw some line in here. Here's our line, L. Good so far? Its angle of inclination is whatever this angle is right here, and we're going to call that theta. Now pick any 2 points on it, P1, P2. We'll call this P1, and we'll call this P2. Good? Our job is to prove that the tangent of theta is equal to y2 minus y1 over x2 minus x1. So I'm going to construct a right triangle using these 2 points. Sorry, terrible. I think you know what I'm trying to draw though, right? Here's our right triangle. What is this distance?
x2 minus x1.
What is this distance?
y2 minus y1.
What is this angle?
0. I forgot what it's called.
Theta.
Yeah, that.
Yeah, this line was intended to be drawn, so this line's parallel to this line. Perfect. Now, by definition, tangent of theta gives you what?
Is it x over y over
Y
x?
over x. That's our definition for tangent over here. That I erased.
Yeah.
Sorry about that. No wonder you didn't see it. So it gives us y over x. So then tangent of theta is equal to y2 minus y1 over x2 minus x1. So tangent of theta is always equal to that for a line going through any 2 points with those coordinates. Cool. All right. Definition of slope. You already have intuition for slope. Now we'll come up with a definition of slope. The slope of a line L that isn't vertical through the points x1, y1, and x2, y2 is given by y2 minus y1 over x2 minus x1. And we typically use the variable m to signify the slope, which you're already used to. You've seen an equation like y equals mx plus b 100 times, right? And the m in that equation was meant to signify the slope. M is a common variable that we use for the slope. Now if you have 2 points on a line, you can always calculate its slope, assuming that the line has a slope. The only line that doesn't have a slope is a vertical line. Okay. L1 and L2 are parallel if and only if M1 is equal to M2. Their slopes are equal. So, how would we prove that really quick? This one you probably don't really know what we can use because we didn't build up from a geometry where we're clear with what we mean by parallel lines, right? But if I have 2 parallel lines, then this angle and this angle are going to be identical. Right? And then so the tangent of those angles are going to be identical. And so the slopes are going to be identical. And then working backwards, if the slopes are identical, the tangents are identical, and so the thetas are identical. And that's the logic behind how you prove that. Make sense? Okay. Points A, B, C are collinear if and only if AB is equal to the slope of AC. So let's make sense of that one really quick. You know what it means for 3 points to be collinear? They all lie on the same line.
Okay.
So I have a point A here, I have a point B here, and I have a point C here. And I'm wondering, they kind of look like they all land on one line, but do they really? Do they really all land on the same line? And how can I check that if I know the coordinates of those points? So points A, B, and C are collinear if the slope of the line AB and the slope of the line AC are the same slope. Does that make sense? So if they're the same slope, then obviously they have the same thetas. And if they have the same thetas, then they're parallel. And parallel lines that intersect are collinear. That's where the geometry would have come in. So I feel like there's a lot of use in proving these the way the author does, because it's like, what can I use to begin with? Which is why I'm not bothering to do his proofs. Okay, but the example now is worth going through. So we have 3 points here, A, B, and C, and the question is, are they actually collinear, and how can we check that? And so you might have before been stumped by this. So if I give you a point 2, 3, here's A. I give you the point 5, 1. Here's B. And I give you the point 11, -3. do those in fact all fall on the same line, and how can we check that? And so the way that we can check that is by checking the slopes in between the two lines. Check the slope between here, and check the slope between here. If they're the same, it's collinear. So what is the slope between here? We're going to do the height of this. So I'll call that M1. M1 will be the slope between these two lines. So M1 is equal to y2 minus y1 over x2 minus x1, right? So, I don't know, I'll call this one the 2. So we have y2 minus y1 over x2 minus x1. Is that a 5? Okay, so there's M1, which is equal to, I guess, simplify really quick. 3 minus 1 is 2 over negative 3. Do that right? Minus 2/3. Okay, now let's check A to C, and we'll call that one M2. M2 is equal to, once again, we're going to have 3 minus the height of this one. Thank you. Over 2 minus the x of this one, which is equal to 6 over 9, negative, right? And then 3's go out top and bottom, leaving me 2 over minus 3. 2 over minus 3, 2 over minus 3. Therefore, they are collinear. There is a single line you could draw through all three of those points. Okay. Our last proof. Let's see if I can do this one. The author proved this one using a trig identity, and I didn't want to go through trig identities because I felt like that would be in one ear and out the other after how much trig we did. So, I'm not sure how I'm going to prove this one yet, is what I'm hinting at. So you might have to help me a little bit. Okay, so first off, I'm going to draw just a dotted line, xy, and you'll see why in a second, because I'm going to want to draw a new one. So, my job is to show that two lines are perpendicular if and only if the slope of the first line is equal to the negative reciprocal of the second line. So in other words, if this one has a slope of 2/3, the other line has to have a slope of negative 3/2. Okay? So I need to draw two lines that intersect, and they have to be lines with slopes, so I can't have one vertical. So any two lines we want, I'm going to call this one L1. I'm going to call this one, try and make it look like they actually intersect at right angles, L2. With me? Now I'm going to draw a new coordinate system just right down through the center of these things to help me reason about it. Which is why I drew my first coordinate system so light, so I won't get confused. Good? Now what? So, I'll construct a triangle, right triangle with this one. Maybe I should have also done this coordinate system outline so that we don't get confused. Sorry. I'm going to redraw just where my lines intersect and a dotted coordinate system through it. Clean up the picture some so that we don't make a mess. So here's L1, and I'll draw L1 more slanted so it's more obvious which is which. Here's L1. Here's L2. And then here's my shifted coordinate system. With me? So I'm going to create a right triangle right here. I'm going to create a right triangle right here. I'm going to call the angle from here to L1, put my L2 up here. I'm going to call the angle from here to L1 theta 1. I'm going to call the angle from here to L2 theta 2. I know that theta 2 is 90 degrees more than theta 1. Not sure how that's going to help, but we'll see here in a second. So I'll pick 2 points, one on L1, one on L2. And in my new coordinate system, this is 0, 0. Because if they're perpendicular at some point, when I shift them to the center of my coordinate system, they should still be perpendicular, right? So this is just going to help make the algebra easier, I think. So this has coordinate 0, 0. I'm going to say this point has coordinates x1, comma y1. I'm going to say this one has coordinates x2, comma, y2. Good so far? All right. So that means that this distance right here is x1, and this distance right here is y1. Because this is my origin 0, 0. Okay, so then my slope m1 is equal to, what's the slope of L1? Just rise over run. It's just y1 minus 0 over x1 minus 0, right? That's the slope between this point and this point, which is just y1 over x1. You follow me? Okay. My second thing to notice is going to be that these are similar triangles. And we'll make that make sense right now. Okay, so this angle right here is theta 1, right? And it's how much this was shifted. We shifted this up theta 1, right? So this angle right here is going to be the same as this angle right here. This is also theta 1. Which is going to be the same as this angle right here, theta 1. Which is going to be the same as this angle right here, theta 1. Because these two lines are supposed to be parallel, even though I didn't draw it that way.
What?
If you have two parallel lines and an intersecting line,
Oh, yeah, I get that. I'm
then that angle is the same as that angle.
like wondering how did you get that theta 1 at the top there?
This one?
Yeah.
So the theta 1 at the top there is because theta 2 is a right angle plus theta 1.
How do you know that's a right angle? Wouldn't that just be your proof then?
Oh, I need to do, if these are a right angle, then we get m1 is equal to m2.
Oh. I thought you were proving it the other way this whole time. Okay.
Okay, so I'm going to start with, that's a right angle, so then m1 has to be equal to m2.
Mhm.
Okay. Okay, so good so far, right? All right. So now, so I was saying that was theta 1, that was theta 1. Since this is theta 1, this right here is also theta 1. You see that? Since it's this line.
Yeah.
Okay. So now I know this angle is the same as this angle, and this angle is the same as this angle, so this angle has to be the same as this angle. So they're similar triangles. So that means that this side length over this side length has to be equal to this side length over this side length. So this is equal to y2 over x2. Is that right? I think so. y1 over x1 is equal to y2 over x2. We're good so far, right? Now, okay, yeah, I see it. We need to think about the slope of L2. The slope of L2 is rise over run. It's this distance over this distance. So it's what I take, if I were to take this triangle and flip it up right here, right? Then now, instead of this distance was y2, this distance is going to be minus y2. But instead of x2, that's going to be minus x2. And we're still in trouble. I'm messing something obvious up. Oh, no wonder. Let's put the triangle around. y1 over x1 is the same as x2 over y2. There we go. Right? Did I do anything weird now? So that's because they're similar triangles. Except where's my sine going to come from? Because I know that m2 has to equal y2 over x2. Right? No, negative y2 over x2.
I'm so confused how you got the first part. Y1 over x1 equals x2 over y2.
Because they're similar triangles. So this side over this side has to be equal to this side over this side.
Those aren't corresponding parts though.
They are. This corresponds to this, and this corresponds to this. Theta 1, 90. Theta 1, 90.
Okay, okay. Kind of see it more now.
Yeah, my picture's not great, but since these two triangles are similar, then the ratio of this over this is equal to the ratio of this over that, which is what we have here, right?
Yeah.
Okay. Now, m2 is just y2 over x2. Right?
No.
Has to be. Because here's our point, x2, y2, and we can calculate its slope as x2 minus 0 over y2 minus 0. But we could have also calculated it as 0 over, but that still gets us two negative signs, not one. Where does our negative sign come from? We're missing something. Because I actually get that this is equal to the negative of that or something like that. Right? Oh, it is equal to the negative of that. And here's how we justify it. This ratio is equal to this ratio when we talk about distances. But x1 and y1 and x2 and y2 are directed distances. Okay, so here's how we justify this one more time from the beginning. When I have any two lines intersecting, if we were to draw their points at the x-axis, one of them has to be at an acute angle. And so whichever one's at the acute angle, I'm going to call that one L1. And then L2 will always be the one not at the acute angle. Which means our triangle down here, we're always guaranteed that this point has negative coordinates. And for our triangle down here, we're guaranteed positive negative coordinates. So to get these two ratios together equal, we have to put a negative sign in there. This is negative. This is positive negative.
I see that, but what if you drew your lines differently? So
I'm saying no matter how you draw your lines, one of them has to be at an acute angle, and the other one has to be at an obtuse angle, no matter how I draw them.
I thought they were perpendicular.
They are perpendicular. But I'm saying, so my first line, however you want me to draw my first line, tell me how you want me to draw it. Which quadrant should I start in?
The second one?
Start here? Okay, so I'm going to draw from here, over here, and now I need to draw one perpendicular to that.
Okay.
So when I draw one perpendicular to that, the angle to the first one, I'm saying now I'm going to call this one L1, and this angle will always be acute. And so the triangle that we make over here will always be negative, negative. And the triangle that we make for L2 now, when we drop it down here, will always be positive, negative. And so if those are similar triangles, to make their ratios equal, I need to add a negative on this one. Does that make sense?
Mm-hmm.
Okay, so that justifies the sign. Perfect. So M1 is equal to negative x2 over y2, which is the same thing as, let's see, negative, try and see how I can best make you see this, x2 over y2, which is equal to negative 1 over m2. Because remember, m2 is just equal to y2 over y1, or y2 over x2. Right, here's the slope of m2, here's the slope of m1. And so I just basically tell m1 is also equal to negative 1 over m2. Good?
Mm-hmm.
All right, so there's that way. If they're perpendicular, then that's the case with their slopes. And I'm not going to prove the other way because I don't have an obvious way to start it in my head. And I don't like the author's way because he just uses trig identities. He uses the fact that when you add 90 degrees to cotangent, it gives you negative tangent. And that's all he does. Which gives you no insight into anything. So we'll end it there. And